Breaking news from the edge of the solar system. Astronomers are reporting an unprecedented surge of comets, 17 in total, appearing just as the interstellar object 3I ATLAS makes its passage. The orbits cluster when ATLAS arrives, then scatter once it leaves, like a cosmic heartbeat. Coincidence, illusion, or hidden influence? Tonight, we investigate this unfolding anomaly. Stay with us until the end, because the deeper you go, the stranger this story becomes. If this mystery has you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and whether you believe we're getting the full truth about these happenings. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. Thank you for having our back. Part 1. The Breaking Claim. Picture this. You open a solar system simulator on your computer, one of those programs that plots orbits like clockwork, dots tracing ellipses through empty space. You press play. The planets glide in their predictable grooves, Jupiter massive and indifferent, Earth spinning its tiny blue circuit. But then you notice something else. A cluster of smaller dots, maybe 17 of them, all drifting inward at the same time. They're comets. They shouldn't be moving like this, shouldn't be converging like a school of fish sensing a predator. But they are, and here's the strangest part. As an object labelled 3I ATLAS crosses into the inner solar system in 2025, these comets seem to move with it, pulsing toward the Sun. Then, as ATLAS begins its exit in mid-2026, they scatter again, drifting back outward like the whole system just exhaled. The solar system seems to breathe. This isn't science fiction. It's a pattern people started noticing in orbital simulations earlier this year. A user named Dobsonian Power posted a thread on social media showing exactly this phenomenon. 17 comets labelled and tracked, all appearing to cluster as ATLAS made its approach. The images spread fast. Other observers chimed in. Stefan Burns, who goes by AstroBurns online, validated what Dobsonian Power was seeing. He said the comets seem to cluster while ATLAS is inbound, then separate again after it passes. This wasn't just one person eyeballing a glitch in the software. Multiple sets of eyes, multiple simulations, same eerie result. So we have to ask the uncomfortable question. Is this coincidence? Is it some quirk of how we visualize orbits, a trick of projection and perspective? Or is something genuinely strange happening? Some hidden coupling between this interstellar visitor and the icy wanderers already in our neighbourhood? Could ATLAS be nudging them somehow, exerting influence we don't yet understand? Are we witnessing echoes of a larger interstellar wave, a cosmic tide washing through our system at precisely this moment in history? The implications fork in every direction. If ATLAS is affecting these comets, we need to understand the mechanism. Gravity alone seems insufficient at these distances, at these relative velocities. If it's not ATLAS doing the nudging, then maybe the comets and ATLAS are both passengers on something bigger, a stream or wave originating far beyond the heliopause. Or maybe, and this is where it gets uncomfortable, we're seeing patterns that aren't there, conjuring coherence from randomness because our brains are wired to find it. But here's what makes this more than idle speculation. We're going to test every plausible path. We'll explore the possibility of Oort cloud waves, gravitational ripples sent inward by some ancient stellar passage. We'll examine whether dark matter subhalos or rogue planets could be funneling comets our way. We'll even touch on the more exotic theories, the ones that ask whether ATLAS might be something other than a natural comet, whether its presence is somehow designed or controlled. And yes, we'll scrutinise whether the entire phenomenon is an artefact of our instruments and our minds, a pattern projected onto chaos. By the end of this investigation, you'll have every piece of the puzzle laid out in front of you. The data, the speculation, the physics, the philosophy, and then you'll get to decide. Is the pulse real? Is it spooky? Or is it just the universe reminding us how little we actually understand about the clockwork we live inside? Stay with me. This gets stranger before it gets clearer. Part 2. 3I ATLAS. What sets this visitor apart? Let's start with what we know for certain. 3I ATLAS, catalogued as Comet C/2025 as 1, is not from around here. Its trajectory is hyperbolic, meaning it's unbound to the Sun. a visitor passing through on a path that will carry it back out into interstellar space. It entered the inner solar system in 2025, moving inbound at speeds consistent with an object originating outside our gravitational neighbourhood. Perihelion, its closest approach to the Sun, is expected around October 30th, 2025, at a distance of roughly 1.4 astronomical units. For reference, Earth orbits at 1 astronomical unit, so ATLAS will pass inside our orbit but not dangerously close. Its nearest approach to Earth will be about 1.8 astronomical units, roughly 270 million kilometres. We're safe. But proximity isn't what makes ATLAS interesting. What makes ATLAS interesting is how it behaves. NASA's Swift Observatory detected something unusual when ATLAS was still about 2.9 astronomical units from the Sun. The comet was losing water at an extraordinary rate, like a fire hose turned on full blast. Most comets don't activate their outgassing until they're much closer to the Sun, where solar radiation heats their icy surfaces enough to sublimate volatiles. But ATLAS was pouring water vapour into space while still relatively distant, suggesting either an unusually volatile composition or some internal heat source we don't fully understand. Then came the spectroscopy. The James Webb Space Telescope turned its infrared eyes on ATLAS and found a coma dominated by carbon dioxide. The ratio of carbon dioxide to water was about 8:1, extraordinarily high compared to typical solar system comets. JWST also detected water vapour, carbon monoxide and carbonyl sulfide in the mix. This chemical signature doesn't match most comets we've studied. It suggests ATLAS formed in an environment with different temperatures, different radiation fields, different processes than the ones that birthed the comets native to our system. Polarimetry added another layer of oddity. The first polarimetric observations of ATLAS revealed a deep, narrow negative polarization branch, reaching negative 2.7% at a phase angle of about 7 degrees. The inversion angle, where polarization shifts from negative to positive, occurred around 17 degrees. These features don't show up in typical solar system comets. Polarization tells us about the size, shape, and composition of dust grains in the coma. ATLAS's polarization signature suggests its dust is structured differently, possibly reflecting a formation history unlike anything in our local population. And then there's the controversial bit. Avi Loeb, the Harvard astrophysicist known for provocative proposals, suggested that ATLAS might emit its own light, meaning it's not just reflecting sunlight, but possibly glowing from some internal process. This claim is speculative and hasn't been verified by independent observations, but it adds to the sense that ATLAS isn't playing by the usual rules. If a comet is glowing on its own, where's the energy coming from? Nuclear decay? Chemical reactions? Something else entirely? These peculiarities matter because they hint at origins. If ATLAS is chemically unusual, if it's volatile in ways our comets aren't, if it's glowing when it shouldn't, then maybe it came from a stellar system with conditions radically different from ours. Maybe it formed in a region with more carbon dioxide ice, less water. Maybe it was irradiated by a different star, baked by cosmic rays during its interstellar journey. Or maybe, just maybe, it's not entirely natural. That's a thread we'll pull later. For now, keep this in mind. ATLAS is strange, and strange objects do strange things. Could its strangeness be connected to the apparent pulse of comets around it? Could these signatures, this unusual chemistry and behaviour, somehow correlate with the movement of other bodies? We're going to find out. Part 3. The 17. Mapping the crowd. So let's talk about the crowd. 17 comets, give or take, depending on which simulation you're watching and which bodies you count. Some are bright, easily visible in amateur telescopes, others are faint smudges at the edge of detectability. But they're all there, moving through the inner solar system during the same narrow window when ATLAS makes its pass. Calling them a fleet feels dramatic, but the word fits. They move together in time, if not exactly in space, like a squadron responding to an unspoken signal. Who are they? The roster includes recently discovered comets with designations like C/2025R2, also known as Swan, and C/2025A6 called Lemon. There's C/2025K1, another ATLAS discovery. Periodic comets are in the mix too, short-period visitors like 414P and 210P that swing through on predictable schedules. Older long-period comets, objects that take centuries or millennia to complete one orbit, are also present, some of them caught mid-loop on their way back out. These are the names we know, the objects bright enough or close enough to catalogue. There are probably others, fainter ones slipping past our surveys. When you plot their perihelion dates, the dates they reach closest approach to the Sun, you get a histogram with a pronounced peak. Late 2025, early 2026. That's the burst window, the period when the inner solar system suddenly gets crowded. Normally, comets arrive in ones and twos, scattered across months or years. But this cluster is dense. It's not unprecedented. Periods of increased comet activity have been documented before, but it's unusual enough to raise eyebrows. Detection plays a role here. Many of these comets were found by the same surveys that operate intensely during this period. ATLAS, the Asteroid Terrestrial Impact Last Alert System, is a network of robotic telescopes designed to scan the sky for near-Earth objects. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, does similar work. SWAN, the Solar Wind Anisotropies instrument on the SOHO spacecraft, detects comets by their hydrogen emission. These surveys are good at their jobs. They find objects, and when they're all operating at full capacity, they find more objects. So part of the apparent burst could be selection bias. We're looking harder, so we're seeing more. But even accounting for that, the clustering feels off. Astronomers who work with comet populations will tell you that seeing 17 comets simultaneously in close-in visualizations isn't normal. It's not impossible, but it's not every day either. And the timing, the fact that this crowd appears just as an interstellar visitor crosses through, adds a layer of discomfort. Coincidences happen. The universe is big, and big systems produce strange alignments by chance. But coincidences also deserve scrutiny. Here's the question that nags. Do these comets move like a flock? Or do they just happen to align in our view because of how we're compressing time and space into simulation frames? Are we seeing an actual dynamical relationship, bodies influencing one another or responding to a common force? Or are we seeing ghosts, the projections of independent orbits that only look synchronized when viewed from a specific angle at a specific moment? The answer isn't obvious. In the next section, we're going to pull apart the simulations themselves, see how they can mislead us, how they can turn random orbits into apparent choreography. But keep this in mind. Even if the pulse is partly illusion, the raw fact remains. A lot of comets are passing through right now, and that, at minimum, is worth explaining. Part 4. Simulation versus reality. Simulations lie. Not on purpose, but by necessity. When you're trying to show the motion of planets, comets, asteroids, all moving at different speeds across different scales, you have to make compromises. You compress time, turning years into seconds. You flatten three-dimensional space into two-dimensional views, projecting orbits onto the ecliptic plane or some other convenient surface. You exaggerate sizes so tiny objects become visible. And in doing all of this, you introduce distortions. What looks like clustering in a simulation might be nothing more than an artifact of projection, objects that are actually separated by millions of kilometers appearing close, because you're looking at them from the wrong angle. This is called ephemeris compression. You're taking orbital data that spans years, maybe decades, and squeezing it into a visual span of minutes or seconds. Motion that's gradual in real time becomes rapid and dramatic in simulation time. Comets that arrive at perihelion months apart can appear to converge if you speed up the clock enough. It's like watching a time-lapse of clouds. Individually they drift. But speed up the footage, and they seem to race and swirl with purpose. Orbital inclination makes this worse. Most planets orbit near the ecliptic plane, the flat disk where Earth's orbit lies. But comets don't follow that rule. They come in at steep angles, diving down from above or below, their paths tilted wildly relative to the planetary disk. When you project these inclined orbits onto a flat view, they can appear to intersect or cluster even when they're nowhere near each other in actual three-dimensional space. Imagine looking at a globe from directly above the North Pole. Lines of longitude converge at the pole, but that's an artifact of perspective. The lines are actually parallel at the equator. Same principle with comet orbits. convergence in projection doesn't equal convergence in reality. So here's the test. You take the same 17 comets, the same ATLAS trajectory, and you rotate the viewpoint. Instead of looking down on the ecliptic plane, you look at the system edge-on, or from some oblique angle. And when you do this, interesting things happen. The pulse weakens. The apparent clustering spreads out. Comets that seem to move together now look independent, each on its own path, crossing through the inner system at its own pace. The flock becomes a crowd of individuals who happen to be in the same neighbourhood, but aren't really interacting. This doesn't mean the pulse is entirely fake. It means the visual impression is unreliable. We have to dig deeper, look at the actual orbital elements, the numbers that define each comet's path, things like semi-major axis, eccentricity, inclination, longitude of ascending node, argument of perihelion. If the comets are genuinely clustering, if there's a physical reason they're all here at once, those numbers should show patterns. Shared inclinations, similar nodes, radiant vectors that point to a common origin. If the numbers are random, then the clustering is likely coincidence plus projection plus detection bias. There's also observer bias. Humans are pattern-seeking. Machines. We see faces in clouds, hear words in static, find meaning in random sequences. When we know there's a strange object in the solar system, an interstellar visitor with unusual properties, our brains start looking for connections. We see the comets moving, we see ATLAS moving, and we link them, even if the link isn't there. It's a cognitive shortcut, useful for survival in most contexts, but a liability when you're trying to extract signal from noise. Detection bias compounds this. Telescope surveys have schedules, target lists, weather constraints. Some regions of sky get scanned more often than others. Some times of year are better for observation. Comets that peak in brightness during windows when surveys are active are more likely to be found. Comets that brighten during seasonal gaps might go unnoticed. So the apparent burst in comet discoveries could reflect the timing of survey activity as much as the actual timing of comet arrivals. Temporal aliasing is another culprit. When you're compressing time, you're sampling motion at discrete intervals. If the sampling rate doesn't match the actual motion, you get aliasing effects, false patterns that emerge from the mismatch. Think of a spinning wheel filmed at the wrong frame rate. The spokes seem to move backward, even though the wheel is spinning forward. Same principle. If your simulation updates every few days, and comets are moving in complex asynchronous patterns, the compression can create apparent synchrony that isn't real. So is the pulse real spatial clustering, or is it largely a cinematic artifact? We don't have a definitive answer yet. What we have is reason for caution and reason for deeper investigation. In the next act, we're going to run real data tests, compare orbital elements, look for radiant vectors, see if any physical pattern emerges from beneath the cinematic veil. Because if the pulse is real, if these comets are genuinely connected to ATLAS or to some larger structure, then we're looking at something significant. And if it's not real, if it's just an illusion born of projection and bias, then that's significant too. It tells us how easy it is to fool ourselves when we're staring at the sky. Part 5. Expert unease and public speculation. Professional astronomers are careful people. They hedge their statements, qualify their claims, resist jumping to conclusions. When you ask them about the comet pulse, you get words like interesting, unusual, worth investigating. You also get phrases like no known mechanism and further work required. This is the language of discipline, the language of people who've seen too many exciting patterns evaporate under scrutiny. They're not dismissing the pulse. They're withholding judgment until the data firms up. But out in the wider world, where excitement moves faster than evidence, speculation blooms, online forums light up with theories. Is ATLAS pulling the comets somehow, exerting gravitational influence despite its relatively small mass? Is this a cosmic signal, a message encoded in orbital mechanics? Could there be an unseen perturber, a dark planet or rogue star nudging things from the shadows? The ideas proliferate, some grounded in physics, others veering into territory where science blurs into fiction. Avi Loeb, predictably, leans into the provocative side. He's floated the idea that ATLAS might not be entirely natural, that its anomalous behaviour could hint at something more than a simple comet. He's careful to frame these as speculations, thought experiments, but the framing doesn't stop the ideas from spreading. Loeb has a history with this kind of thinking. He suggested that Oumuamua, the first confirmed interstellar object might have been an alien probe or light sail. That claim divided the astronomical community, some praising his willingness to think outside conventional boundaries, others accusing him of attention-seeking. With Atlas, he's treading similar ground. If the comet is glowing on its own, if it's outgassing in ways that don't fit models, maybe we should at least ask whether it's more than a chunk of ice and rock. History offers cautionary tales. The Kreutz Sungrazers, a family of comets that dive extremely close to the Sun, once spawned wild speculation about their origin and purpose. People wondered if they were remnants of a destroyed planet or artifacts of some catastrophic event in the inner solar system. Turns out they're fragments of a single parent comet that broke apart centuries ago, nothing more exotic than gravitational erosion and tidal stress. But for a while, they fed the imagination. Conspiracy thinking thrives in data gaps. When evidence is thin, when mechanisms aren't clear, people fill the void with narratives. Some invoke dark matter, imagining invisible structures that funnel comets like tributaries into a river. Others reach for artificial explanations, proposing that Atlas is a probe or beacon sent by an intelligence we haven't yet contacted. These ideas aren't inherently absurd, the universe is strange enough to permit wildness, but they require extraordinary evidence, and right now the evidence is ordinary. Odd, yes. Unexplained, sure, but not yet extraordinary. Scientists put boundaries around speculation. They ask what can be tested, what predictions each hypothesis makes, what observations would falsify it. This discipline is protective. It keeps us from chasing every shiny pattern down a rabbit hole. But it also means that when something genuinely anomalous appears, the response can seem slow, overly cautious. The public wants answers now. Science offers probabilities and error bars. In the next act, we're going to lay out a buffet of hypotheses. Oort cloud waves, interstellar debris streams, dark perturbers, even the artificial object angle. You'll get to weigh them, see which ones hold water and which ones collapse under their own weight. We're not going to shy away from the weird. But we're also not going to abandon rigor. By the end, you'll have all the pieces, and you'll decide how weird you want to believe. Because the universe doesn't care what we believe. It just keeps doing what it does, indifferent to our attempts to categorize it. And sometimes, that indifference looks a lot like mystery. Part 6. The Oort cloud wave hypothesis. Imagine a vast sphere surrounding the solar system, stretching halfway to the nearest star. It's made of ice. Trillions of icy bodies tumbling slowly in the dark, bound to the sun by the faintest threads of gravity. This is the Oort cloud, the reservoir from which long-period comets originate. Most of these objects will never see the inner solar system. They'll drift in frozen silence for billions of years, undisturbed. But occasionally, something shakes them loose. A passing star, a gravitational ripple from the galactic disk, a massive gas cloud threading through the sun's neighbourhood. When that happens, a packet of comets gets nudged inward, falling toward the sun on timescales of thousands or millions of years. This is the Oort cloud wave hypothesis. The idea is simple. Some past event, maybe a stellar flyby or a tide from the Milky Way structure, sent a wave of perturbations through the Oort cloud. That wave propagated inward, and now, in 2025, the crest of that wave is reaching the inner solar system. The 17 comets we're seeing aren't responding to Atlas. They're riding the wave, and Atlas just happens to be arriving at the same time. Coincidence, but of the grand cosmic sort, where timescales align by chance. We have candidate perturbers. Gliese 710, a red dwarf star, is projected to pass within about 16,000 astronomical units of the Sun in roughly 1.3 million years. That's close enough to stir the outer Oort cloud, sending cascades of comets inward. Models suggest that such a passage could increase the flux of long-period comets by a factor of several over a span of thousands of years. But Gliese 710 hasn't arrived yet. So if it's the culprit, the wave we're seeing now would have to be from an earlier, less well-documented passage by some other star. There are older candidates. Stars pass through the Sun's vicinity roughly every few million years. Some are documented in astronomical catalogues, their trajectories reconstructed from proper motion and radial velocity data. Others are lost to time, their close approaches happening before we had instruments to record them. Any of these could have triggered a wave. The question is timing. Did the wave crest arrive now, or is this just a background fluctuation in comet activity? The wave hypothesis has appeal. It explains why multiple comets are inbound without requiring Atlas to do anything. Atlas is just another passenger, a piece of interstellar debris that happened to cross our path during the same era when a Oort cloud. Wave was peaking. It removes the need for exotic coupling mechanisms, for gravitational tricks or electromagnetic interactions. The comets aren't responding to Atlas. They're responding to a perturbation that happened long before Atlas entered our neighbourhood. But the hypothesis has weaknesses. First, the timing has to be extraordinarily fine-tuned. The crest of the wave, the moment when the most comets arrive, has to align with Atlas's passage within a window of months. That's possible, but improbable. Second, comets in a wave driven by a single perturber should show some coherence in their orbital elements. They should have similar semi-major axes, similar inbound velocities, maybe even similar inclinations if the perturber came from a specific direction. If the 17 comets are a random assortment of long-period and short-period objects with no common origin, the wave hypothesis weakens. So how do we test it? We look at the orbital elements, we calculate where each comet came from, how long ago it was perturbed, whether its trajectory points back to a common epoch or direction. If they cluster, if there's a signature of a shared disturbance in their motion, the wave hypothesis gains credibility. If they're scattered, if their orbits suggest independent perturbations at different times from different directions, the wave hypothesis struggles. There's also the question of amplitude. A wave strong enough to send 17 comets inwards simultaneously should leave other traces. We should see an elevated background rate of comet discoveries, not just a spike in 2025. We should see objects arriving from a preferred direction, a radiant in the sky where the wave originated. Surveys like Pan-STARRS and ATLAS, which have been operating for years, should have recorded the ramp-up, the gradual increase in comet flux leading to the current peak. If that ramp-up exists in the data, it supports the wave. If the spike appears sudden, isolated, it suggests something else. In the next section, we're going to zoom in on the orbital details, see if any of the 17 comets share alignments, inclinations, or radiant vectors consistent with a streaming origin. Because if they do, we might be looking at more than a wave. We might be looking at a debris train, a family of objects with a common parent, fragmented and spread along a shared trajectory. And if Atlas is part of that train, then the pulse isn't just coincidence, it's a signature of kinship, a cosmic family reunion playing out in the inner solar system. Stay with me, the orbits hold clues. Part 7. Streams, Families and Debris Trains. Comets can have relatives, not in a biological sense, obviously, but in the sense that some comets originate from the same parent body. A large comet passes close to the Sun, tidal forces tear it apart, and the fragments spread along the original orbit like beads on a string. Over time, those fragments drift, perturbed by planets and radiation pressure, but they retain a family resemblance in their orbital elements. The Kreutz sun grazers are the most famous example. Dozens of comets, all diving to within a few solar radii of the Sun, all fragments of a single ancient progenitor that broke apart centuries ago. Could Atlas and the 17 comets be part of a similar structure? Could they be passengers on a larger interstellar debris stream, pieces of some fragmented object that entered the solar system together? The idea has appeal. It would explain the temporal clustering without requiring fine-tuned coincidences or exotic physics. Atlas and the comets aren't independent visitors. They're siblings, separated by distance but bound by origin. To test this, we need to look at orbital elements in detail. Specifically, we need to compare inclination, longitude of ascending node, and argument of perihelion. Inclination tells us the tilt of the orbit relative to the ecliptic plane. Longitude of ascending node tells us where the orbit crosses the ecliptic going northward. Argument of perihelion tells us the orientation of the orbit's long axis. If comets share a common origin, if they're fragments of a single parent, these elements should cluster. Not perfectly, perturbations will have scattered them, but enough to reveal the underlying relationship. We also look at radiant. Radiant is the point in the sky from which a comet appears to originate, the direction its velocity vector points when you trace it backward. For meteor showers, radiant is obvious. All the meteors seem to stream from a single point because they're particles in a shared orbit, debris from a comet that passed through earlier. For comets, radiant is subtler, but it's still calculable. If multiple comets share a radiant, especially if that radiant aligns with Atlas's inbound direction, it suggests a streaming origin. Preliminary analysis based on publicly available orbital data shows mixed results. Some of the 17 comets have similar inclinations, clustering around 30 or 40 degrees, but others are scattered from 10 degrees to nearly 90 degrees. The longitude of ascending node values are all over the map, suggesting no preferred direction of entry. Argument of perihelion varies widely. At first glance, the orbital elements don't scream family, they scream randomness, but orbital uncertainties matter. For newly discovered comets, especially faint ones detected only a few times, the orbital elements have large error bars. A comet that appears to have an inclination of 30 degrees might actually be anywhere from 25 to 35 degrees, depending on the quality of the observations. When error bars are large, apparent scatter can hide real clustering. We'd need high-precision astrometry, multiple observations over weeks or months, to pin down the orbits well enough to see family relationships. There's another wrinkle. If ATLAS triggered fragmentation in a passing debris stream, the offspring comets might not share ATLAS's exact orbit. Imagine a loose rubble pile, a cluster of icy fragments bound together weakly, crossing the solar system. ATLAS is the largest piece, bright enough to be detected from far away. But as it approaches the sun, solar radiation and tidal stress shake the pile apart. Smaller fragments drift away, following slightly different paths. They reach perihelion at different times, appearing as independent comets. But they're not independent. They're pieces of the same structure. This scenario makes predictions. The smaller comets should appear along ATLAS's trajectory, slightly ahead or behind, slightly offset in inclination. Their composition should match ATLAS's composition, the same high carbon dioxide to water ratio, the same spectroscopic signatures. If we observe these smaller comets with JWST or other high-resolution instruments, we should see family resemblance in the chemistry. So far, detailed spectroscopy of the 17 comets is limited. Most are too faint for JWST follow-up, at least with current observing schedules. But if any of them brighten, if they become accessible targets, we can test the debris train hypothesis directly, match the chemistry, and the case for a shared origin gets much stronger. There's also the possibility that some of the 17 are known stream members, comets that belong to established families. For example, if one of them turns out to be a Kreutz sungrazer, that's informative. It tells us that at least part of the burst is unrelated to ATLAS, just background activity from pre-existing streams. If none of them are known family members, if they're all long-period comets with no prior affiliation, that shifts the interpretation. It makes the burst look more like a genuine anomaly, something requiring explanation beyond normal solar system dynamics. In the next section, we're going to venture into darker territory. Literally. We're going to talk about invisible perturbers, unseen masses that could be funneling comets inward. Dark matter subhalos, rogue planets, Planet 9, objects we infer from their effects rather than observe directly. Because if the comets aren't streaming, if they're not riding an Oort cloud wave, then maybe something else is shepherding them, something we haven't seen yet. Part 8. Dark perturbers and phantom theories. What if the perturber isn't a star? What if it's something we can't see directly? Something that interacts only through gravity? This is where dark matter enters the conversation. Dark matter, the invisible substance that makes up about 85% of the universe's matter, doesn't emit light. It doesn't absorb light. It doesn't interact electromagnetically at all, as far as we know. But it does have mass, and mass means gravity. And gravity, over long enough timescales, can nudge comets. Dark matter isn't uniformly distributed. Simulations suggest it clumps into subhalos, smaller concentrations of mass embedded within the larger galactic halo. These subhalos range in mass from a few thousand solar masses down to maybe the mass of a planet. Most of them are empty. No stars, no gas, just dark matter particles interacting gravitationally with one another and with normal matter. If one of these subhalos passed through the Oort cloud, it could perturb a swath of comets, sending them inward on paths that converge over millennia. The idea is speculative. We've never directly detected dark matter subhalo. We infer their existence from gravitational lensing, from the distribution of galaxies, from the behavior of stars in the Milky Way's outer regions. But on smaller scales, in the solar system's immediate neighbourhood, we have no confirmed detections. That doesn't mean they're not there. It just means they're hard to find. They're the ultimate stealth objects, interacting only through gravity, leaving no electromagnetic signature. Could a subhalo explain the comet pulse? Maybe. If a subhalo passed through the inner Oort cloud a few thousand years ago, it could have seeded a packet of comets on inbound trajectories. Those comets are arriving now in 2025, and Atlas's path happens to intersect that zone. The subhalo itself is long gone, millions of astronomical units away, but its gravitational footprint remains in the comet's motion. The problem with this hypothesis is testability. How do you detect a subhalo after it's left? You can't look for light because there isn't any. You can look for gravitational effects, subtle perturbations in the orbits of outer solar system objects, but those perturbations are tiny and hard to distinguish from noise. You'd need extremely precise astrometry over decades to see the signature. There's also the question of frequency. If dark matter subhalos are common, if they pass through the Oort cloud regularly, we should see periodic spikes in comet activity, bursts separated by thousands or millions of years. Historical records, both modern and ancient, don't show clear evidence of such periodicity. Comet rates fluctuate, but the fluctuations seem random, not cyclic. That doesn't rule out subhalos. It just means that if they're responsible, they're either rare or small enough that their effects are subtle. Then there's the rogue planet angle. Rogue planets are objects with planetary mass that don't orbit a star. They were either ejected from their birth systems during formation, or formed in isolation in molecular clouds. Simulations suggest there could be billions of rogue planets in the Milky Way, drifting through interstellar space. If one passed through the Oort cloud, it would behave like a dark perturber, nudging comets without being seen. But rogue planets aren't completely dark. They emit thermal radiation, faint infrared glow from leftover heat. Surveys like WISE, the Wide Field Infrared Survey Explorer, have looked for such objects and found a few candidates, but none close enough to the Sun to explain the comet pulse. If a rogue planet caused this, it was either too small to be detected, or it passed through before WISE started observing. Planet 9, the hypothetical super-Earth orbiting in the outer solar system, is another candidate. Planet 9 is invoked to explain the unusual orbital clustering of trans-Neptunian objects, bodies beyond Neptune with aligned perihelia. If Planet 9 exists, it could perturb Oort cloud comets on timescales of tens of thousands of years. But Planet 9 is supposed to orbit in a relatively stable region, not pass through the Oort cloud like a rogue interloper. Its gravitational influence would be steady, not sudden. It doesn't naturally explain a burst in 2025 unless the burst is part of a longer-term trend we haven't noticed yet. Occam's razor pushes back against these ideas, invoking invisible perturbers, whether dark matter, subhalos, or rogue planets, requires adding entities to the model without direct evidence. It's more parsimonious to assume the comet pulse is a combination of detection bias, coincidence, and natural fluctuation in comet activity. But parsimony isn't proof. The universe doesn't owe us simple explanations. Sometimes the truth is weird. If you wanted to test for dark perturbers, here's what you'd look for: anomalous orbital energy in the comets, velocities or trajectories that don't match expected perturbations from known planets, micro-lensing events, brief brightenings of background stars as a massive dark object passes in front of them, residual perturbations on the orbits of outer planets or trans-Neptunian objects, tiny deviations that accumulate over time. These are faint signals, needle-in-haystack searches, but they're within the reach of current or near-future instruments. The bottom line is this: dark perturbers are a possibility, not a probability. They're the kind of explanation you reach for when conventional mechanisms fail, when the data forces you into uncomfortable territory. Right now, the data hasn't forced us there yet. The comet pulse is strange, but not so strange that we need to invoke invisible masses. But keep the idea in your back pocket, because if the pulse persists, if more comets keep arriving in correlated patterns, if the conventional explanations keep falling short, then maybe we'll have to look for shadows. And in the next section, we're going to look at the wildest shadow of all. The idea that Atlas isn't just a comet. The idea that it might be something designed. Part 9, the artificial object angle. Let's be clear from the start, this is speculation. It's the kind of idea that gets floated in late-night conversations between astronomers who've had too much coffee. The kind of thought experiment that pushes boundaries without claiming certainty. But it's worth exploring, if only to understand why it's tempting, and why it's probably wrong. Here's the premise. What if Atlas isn't a natural comet? What if it's an object engineered by an intelligence we haven't contacted? A probe or beacon designed to traverse interstellar space, and interact with planetary systems it encounters? What if its unusual properties, the anomalous outgassing, the strange chemistry, the possible self-emission, aren't accidents of formation but features of design? And what if the comet pulse, the apparent clustering of 17 bodies around its arrival, is part of that design? A response triggered by Atlas's presence? Avi Loeb has made his career, or at least a significant chunk of it, exploring ideas like this. He was the loudest advocate for the possibility that Oumuamua, the first confirmed interstellar object detected in 2017, might be artificial. He pointed to its unusual shape, its trajectory, its tumbling motion, its slight acceleration as it left the solar system. None of these features definitively proved artificiality, but they were odd enough to warrant asking the question. Atlas, with its own set of oddities, invites similar questions. What would it take for Atlas to be artificial? First, it would need an internal energy source, something powering its outgassing and possible self-emission. Natural comets get their energy from solar radiation, which heats the surface and sublimates ices, but Atlas was outgassing intensely at 2.9 astronomical units, farther out than most comets activate. If it's artificial, maybe it has an onboard power system, nuclear decay or fusion or something more exotic, driving the activity. Second, it would need trajectory control, the ability to adjust its path to target specific systems or maintain a desired course. Natural objects follow ballistic trajectories, determined entirely by gravity and initial velocity. Artificial objects can make corrections, firing thrusters or adjusting solar sails. Atlas's trajectory appears ballistic so far, no obvious signs of propulsion, but subtle course changes could be happening at levels below current detection thresholds. Third, it would need a mechanism to influence other bodies, to trigger or modulate the comet pulse. This is the hardest part. How would an artificial object nudge 17 comets simultaneously? Gravity is too weak unless Atlas is far more massive than it appears. Electromagnetic fields could, in theory, interact with ionized material in cometary comas, but the distances involved make this implausible. Radiation pressure, directed beams of light or particles could exert force, but again, the energy requirements seem prohibitive. Maybe Atlas isn't nudging the comets directly. Maybe it's activating them, triggering sublimation in bodies that would otherwise remain dormant. If Atlas emits intense radiation, ultraviolet or X-rays, it could heat nearby comets, causing them to outgauss and become visible. This would create the appearance of a pulse, comets lighting up as Atlas passes, then fading as it moves away. But the distances are still a problem. Atlas is millions of kilometers from most of the 17 comets. Radiation diffuses, weakens with distance. For Atlas to heat comets at that range, it would need to be extraordinarily luminous, far brighter than any natural comet. There's also the question of motive. If Atlas is artificial, why is it here? What's its purpose? Reconnaissance, mapping out planetary systems and their contents. Terraforming, seeding systems with volatiles or genetic material. Communication, broadcasting signals we haven't yet detected. Or maybe it's a relic, an ancient probe sent by a civilization long extinct, still carrying out its mission on autopilot. These are stories, not theories. But stories can frame questions. If Atlas is artificial, what should we be looking for? What tests would distinguish design from accident? One test is structure. Artificial objects often have geometric features, straight lines, right angles, symmetry. Natural comets are irregular, lumpy, the products of random accretion and collisions. High-resolution imaging of Atlas, if we can get it, would reveal its shape. Telescopes like Hubble or adaptive optic systems on large ground-based telescopes could resolve Atlas at perihelion, see whether it's a potato-shaped rubble pile or something more organised. Another test is spectroscopy. Artificial materials, metals, polymers, ceramics have distinct spectral signatures. Natural comets are dominated by ices, silicates, organic compounds. If Atlas's spectrum shows traces of aluminum, titanium, carbon composites, elements or molecules that don't fit cometary models, that would be significant. So far, JWST's spectroscopy shows carbon dioxide, water, carbon monoxide, carbonyl sulfide, all natural, all consistent with a comet. But JWST observed Atlas when it was far from the sun, covered in ice and dust. Close-in observations might reveal something hidden. A third test is signals. If Atlas is a probe, it might be transmitting. sending data back to its origin or broadcasting to any listeners in range. Radio telescopes, like the Very Large Array or the Green Bank Telescope, could scan ATLAS for artificial signals, modulated emissions that don't match natural processes. So far, no such signals have been reported. But the search requires knowing what frequency to look at, what modulation scheme to expect. It's like trying to tune into a radio station without knowing its frequency or language. The counter-arguments are strong. Mass estimates for ATLAS, based on its brightness and assumed albedo, suggest it's a typical comet-sized object, maybe a few kilometres across. That's too small to house complex machinery or significant energy reserves. Trajectory analysis shows no deviations from a ballistic path, no signs of propulsion or course corrections. Chemical composition, while unusual, still falls within the range of natural variation seen in other comets. And the lack of clear propulsion, signatures, the absence of detectable signals, the failure to see any obvious structural features all argue against artificiality. But absence of evidence isn't evidence of absence. A sufficiently advanced probe might be indistinguishable from a natural object, its technology so refined that it mimics nature perfectly. Or maybe artificiality is the wrong word. Maybe ATLAS is semi-natural, a comet that was captured and modified by an intelligence, given a nudge toward our system for reasons we can't fathom. These are ideas at the edge of plausibility, thought experiments that test the boundaries of what we're willing to consider. The meta point is this. The artificial object angle forces us to ask what we're assuming when we interpret observations. We assume comets are natural because every comet we've studied closely has been natural. But our sample size is small, maybe a few dozen comets imaged in detail, a few hundred characterized spectroscopically. The universe contains trillions of comets. Maybe some aren't natural, maybe intelligence, wherever it arises, sends probes into the cosmos, and occasionally those probes cross our path. Oumuamua might have been one, ATLAS might be another, or neither. The point is to stay open, to test rather than assume, to let the data guide us even when it whispers uncomfortable possibilities. In the next section, we're going to step back, look at the bigger picture. Maybe the pulse isn't about the sky at all. Maybe it's about us, about how we see, how we detect, how we interpret. Maybe the pattern is in our instruments, our algorithms, our minds. Because sometimes the most interesting mysteries aren't out there. They're in here, in the space between observation and understanding. Part 10. The meta layer. Are we seeing the sky differently? Here's an uncomfortable thought. What if the comet pulse is real, but not in the way we think? What if it's not a feature of the solar system, but a feature of how we're observing the solar system? What if we're creating the pattern ourselves through the way we detect, classify and visualize objects? Start with detection bias. The surveys that find comets, ATLAS, Pan-STARRS, SWAN aren't passive observers. They're active instruments with specific capabilities, schedules and limitations. ATLAS scans the sky every few nights, looking for moving objects that change brightness or position. Pan-STARRS does similar work with slightly different filters and cadence. SWAN detects hydrogen emission from cometary comas, a different detection method entirely. Each survey has optimal windows, times of year and regions of sky where it works best, and those windows overlap in complex ways. In 2025, these surveys are operating at peak capacity. Funding is stable, instruments are calibrated, pipelines are refined. They're finding more objects because they're better at finding objects. The 17 comets aren't necessarily more numerous than comets in previous years. They're more detected. We're seeing them because we're looking harder, with better tools, at the right times. Then there's algorithmic bias. Modern surveys use machine learning pipelines to sift through data, identifying candidates for follow-up. These algorithms are trained on known objects, taught to recognize patterns that match comets, asteroids, supernovae. They're good at their jobs, but they're not perfect. They have thresholds, cutoffs, that determine what gets flagged as interesting and what gets discarded as noise. If those thresholds change, if the algorithms are updated or retrained, the discovery rate changes. An interesting result came out of Oxford and Google Cloud recently. Researchers trained a general-purpose AI model, Gemini, to classify sky changes and cosmic events. The model could identify transients, explain its reasoning, and flag unusual activity without being explicitly programmed for specific object types. This is exciting. It means AI can help astronomers process the flood of data coming from modern surveys, but it also means AI can introduce subtle biases. If the model sees a pattern, if it starts clustering alerts around a particular time or region, it might amplify that pattern, making it seem more significant than it is. Another Oxford study focused on supernova alerts. They used AI to filter out false positives, reducing astronomer workload by 85%. Again, exciting, but also slightly unsettling. What if the AI is filtering out real events that don't match its training data? What if it's missing comets that behave unusually, objects like ATLAS that don't fit standard templates? The line between noise reduction and signal suppression is thinner than we'd like. There's also temporal clustering in the data itself. Surveys operate on schedules. They observe certain fields on certain nights. Weather, moon phase, instrument maintenance, all affect when data gets collected. If comets are discovered during a narrow window, it might reflect the survey schedule more than the comet arrival rate. Imagine a police department that only patrols certain neighbourhoods on weekends. Crime statistics would show weekend spikes in those neighbourhoods, not because crime is actually spiking, but because that's when police are present to record it. Visualization plays a role too. The simulations that show the comet pulse are built from orbital data, but they're rendered with choices. Time compression, viewing angle, colour schemes, object sizes. These choices aren't neutral, they shape perception. A simulation that updates every day looks different from one that updates every hour. A view from above the ecliptic looks different from a view edge-on. The pulse might be strong in one rendering, weak in another. Which one is correct? Both and neither. They're different projections of the same underlying data. Then there's human cognition. We see patterns even when they're not there. Apophenia, the tendency to perceive connections between unrelated things, is hardwired into our brains. It's useful for survival, helping us spot predators in foliage or allies in crowds. But it's a liability in science, where we need to distinguish real correlations from random noise. When we know ATLAS is in the system, when we're primed to look for effects, we're more likely to see them, even if they're not there. Philosophically, this raises a question. Is there an objective sky, a true state of the solar system independent of our observations? Or is the sky we see always mediated, always filtered through our instruments, our algorithms, our perceptions? Quantum mechanics hints that observation affects reality at the smallest scales. Maybe something similar happens at cosmic scales, not through quantum effects, but through the limits of detection and interpretation. The solar system doesn't care how we observe it, but what we see depends entirely on how we look. Imagine a thought experiment. You have an alien civilization observing the same events from a different star system. They have different instruments, different survey strategies, different biases. Would they see the comet pulse? Or would they see a completely different pattern, or no pattern at all? If the pulse depends on the observer, is it real? The answer isn't simple. Patterns can be real even if they're observer-dependent. A rainbow is real, even though it depends on your position relative to the sun and the rain. The comet pulse might be similar, a real configuration of orbits that only becomes visible when viewed from Earth with specific instruments during a specific window. Real, but contingent. Real, but not absolute. So where does that leave us? With caution. The pulse might be telling us something about the solar system, or it might be telling us something about ourselves, about the limits of our perception, and the biases in our methods. Probably it's both. The comets are really there, their orbits are real, but the impression of synchrony, the sense of a pulse, might be amplified by how we're looking. In the final act, we're going to widen the lens, bring in cosmic news from 2025 that echoes the themes we've explored. Pulses, waves, synchrony. The universe breathing in ways we're only beginning to detect. Stay with me. The weirdness isn't over. Part 11. Gravitational wave surprises. The universe pulses, not just with comets, but with gravity itself. Gravitational waves, ripples in space-time caused by accelerating masses, carry information about the most violent events in the cosmos. Black hole mergers, neutron star collisions, the explosive deaths of massive stars. These events send waves propagating outward at the speed of light, stretching and squeezing space-time as they pass. And in 2025, we're detecting them at an unprecedented rate. LIGO, the Laser Interferometer Gravitational Wave Observatory. along with its partners Virgo in Italy and Kagra in Japan, have been listening to the universe's gravitational symphony for nearly a decade. The first detection came in 2015. Two black holes spiralling together and merging in a cataclysm that shook space-time across 1 billion light-years. Since then, the catalogue has grown. Dozens of black hole mergers, several neutron star collisions, each one adding a note to the cosmic song. But 2025 marks a shift. Detectors are more sensitive now, upgraded with better lasers, improved mirrors, quieter seismic isolation. They're seeing fainter signals, more distant events, mergers involving objects we couldn't detect before. Intermediate mass black holes, objects with masses between 100 and 1,000 times the Sun's mass, are showing up in the data. These are the missing link in black hole evolution, too massive to form from single stars, too small to be the supermassive giants at galaxy centres. We've suspected they exist, but direct detections were elusive. Now we're finding them. There's also a push to open the millihertz frontier, gravitational waves with frequencies between 1,000th and 1/10 of a hertz. Current ground-based detectors can't reach those frequencies. Seismic noise drowns the signal. But space-based detectors, like the planned LISA mission, will be able to listen in this range. They'll detect waves from supermassive black hole mergers, from compact binaries in our galaxy, from processes in the early universe. It's like opening a new window on the sky, except instead of light, it's space-time itself. The connection to the comet pulse is abstract but compelling. Both phenomena involve periodic motion, objects moving inward and outward, systems pulsing with energy. Comets fall toward the sun, black holes spiral toward each other. The scales are wildly different. One happens over years, the other over milliseconds. But the underlying physics is similar. Gravity pulls, orbits decay, energy gets radiated away. In the case of black holes, that energy is gravitational waves. In the case of comets, it's mostly heat and light, sublimated volatiles glowing in the sun's warmth. Could there be a hidden coupling between comet influx and gravitational wave events? Almost certainly not. Gravitational waves from black hole mergers billions of light-years away are incomprehensibly weak by the time they reach us, stretching space-time by less than the width of a proton. They're not going to nudge comets, but the parallel is interesting. The universe operates in pulses on every scale driven by gravity and the motion of mass. Comets pulse inward, black holes pulse together, galaxies pulse as they orbit in clusters. Maybe pulsing is a fundamental mode, a rhythm the cosmos can't escape. There's also a philosophical angle. Gravitational waves let us see events that were previously invisible. Black holes don't emit light. Before gravitational wave astronomy, we inferred their existence from the motion of nearby stars or the glow of accretion disks. Now we detect them directly, through the ripples they make in space-time. Could there be other invisible phenomena, structures or processes we're not detecting, because we don't have the right instruments? Dark matter subhalos, interstellar streams, exotic fields. Maybe the comet pulse is evidence of something similar, a phenomenon we're only glimpsing through its gravitational effects, waiting for the right detector to make it clear. In the next section, we're going to shift focus, look at exoplanet atmospheres and what they're teaching us about planetary system formation. Because Atlas, with its bizarre chemistry, might be a fragment of a system very different from our own. And understanding those systems, understanding how planets form around other stars, gives us context for what Atlas could represent. It's another piece of the puzzle, another way the universe pulses with information. Part 12. Exoplanet Atmosphere Breakthroughs. 2025 is a landmark year for exoplanet science, a turning point in our ability to study worlds beyond our solar system. The James Webb Space Telescope, operating at full capacity after years of commissioning and calibration, is turning its infrared gaze on the atmospheres of distant worlds with unprecedented precision. It's detecting molecules we've only dreamed of finding, piecing together the chemical signatures of planets orbiting other stars, reading their compositions across gulfs of dozens or hundreds of light-years. And what it's finding is forcing us to rethink how planetary systems form and evolve, challenging assumptions we've held since we first started discovering these alien worlds in the 1990s. One recent headline involved a super-Earth, a planet with several times Earth's mass, orbiting a star about 50 light-years away. The planet itself isn't visible directly. It's too small and too dim compared to its parent star. But JWST's spectroscopy revealed something remarkable. As the planet passed in front of its star during a transit, starlight filtered through the planet's atmosphere on its way to us. That light carried fingerprints, absorption lines at specific wavelengths corresponding to molecules in the atmosphere. JWST's instruments revealed carbon dioxide and water vapour in the atmosphere, along with hints of methane and possibly ammonia, molecules that tell a story about the planet's formation and evolution. This is exciting because it tells us the planet has a thick atmosphere, one capable of retaining volatiles over billions of years, despite the intense radiation from its nearby star. It suggests the planet formed farther from its star, out where temperatures were cold enough for ices to condense into solid grains. Those icy grains accumulated into a planetary core, then migrated inward to the current orbit through interactions with the protoplanetary disk, or gravitational exchanges with other planets. Or maybe it formed in place, closer to the star, and was bombarded by comets after formation, icy bodies delivering water and organics in a late heavy bombardment phase, similar to what Earth experienced billions of years ago. The carbon dioxide to water ratio in this planet's atmosphere is unusual, not as extreme as Atlas, but higher than Earth's ratio. Earth's atmosphere is mostly nitrogen and oxygen, with only trace amounts of carbon dioxide, less than 0.1%. But this exoplanet shows carbon dioxide as a major component, suggesting formation conditions very different from our own. It hints at formation in a region where carbon dioxide ice was abundant, maybe in a protoplanetary disk with intense radiation from the star or nearby massive planets. Radiation that preferentially destroyed water molecules while leaving carbon dioxide intact, or temperatures where carbon dioxide could condense but water remained gaseous. This is relevant to our investigation because Atlas has an extreme carbon dioxide to water ratio, about 8:1, far more skewed than this exoplanet but pointing in the same direction. If Atlas formed in a system with similar conditions, around a star that irradiated its disk heavily, or in the outer regions of a carbon-rich disk where carbon dioxide ice dominated over water ice, then its chemistry might reflect that alien environment. It's a window into the conditions around another star, a star we may never identify because Atlas has been travelling through interstellar space for who knows how long, its origin obscured by time and distance. JWST is also detecting more exotic molecules in exoplanet atmospheres, pushing into territory that seemed impossibly ambitious just a few years ago. Sulfur compounds like hydrogen sulfide and sulfur dioxide, which smell terrible, the rotten egg stench of volcanic emissions, but reveal important information about volcanic activity and atmospheric chemistry. These molecules tell us about the planet's interior, whether it's geologically active, whether it has plate tectonics or massive volcanic eruptions pumping gases into the atmosphere. They tell us about photochemistry, how stellar radiation breaks apart and recombines molecules, creating species that wouldn't exist in thermodynamic equilibrium. Organic hazes are showing up too, layers of complex hydrocarbons that scatter light and give some planets their distinctive colours, oranges and reds reminiscent of Saturn's moon Titan. These hazes form when methane and other simple organics are bombarded by ultraviolet light, fragmenting and recombining into larger molecules, polymers that drift down through the atmosphere like smog. The presence of organic hazes suggests chemistry that could be prebiotic, building blocks that might, under the right conditions, lead to more complex molecules and eventually to life. Even potential biosignatures are being tentatively detected, molecules like dimethyl sulfide that on Earth are primarily produced by life, by marine phytoplankton releasing sulfur compounds as metabolic waste. Finding dimethyl sulfide in an exoplanet atmosphere wouldn't prove life exists there. The molecule can form through non-biological processes under certain conditions. But it would be tantalizing, a signature worth following up with more observations, searching for complementary molecules or patterns that strengthen or weaken the biological hypothesis. These detections are tentative, requiring follow-up observations to confirm, but they're pushing the field into new territory where we might actually find evidence of life beyond Earth within our lifetimes. What does this have to do with the comet pulse? Maybe nothing directly. Exoplanets are light years away. Atlas and the 17 comets are right here in our solar system. But it provides crucial context, a framework for understanding Atlas's strangeness. Atlas is an interstellar visitor, an object that formed around another star in another protoplanetary disk, under conditions we can only infer from its observable properties. We can't travel to its birth system, can't study the star that created it, can't map the disk where it accreted. But by studying exoplanet atmospheres, by mapping the diversity of planetary chemistries across the galaxy, we're learning what kinds of environments produce what kinds of volatiles, what stellar conditions lead to carbon-rich versus oxygen-rich systems, what disk temperatures and radiation fields favour certain molecular ratios. We're building a library of formation histories, a reference set against which we can compare objects like ATLAS. If ATLAS's chemistry matches the chemistry of atmospheres around planets in carbon-rich systems, systems with high carbon to oxygen ratios in their disks, that tells us something profound about where it came from. We could narrow down the stellar types, identify whether it formed around a red dwarf, a sun-like star, or something more exotic. If its isotopic ratios, the relative abundances of different isotopes of hydrogen, carbon, oxygen, match patterns seen in specific types of stars or specific regions of the galaxy, we can narrow down the possibilities even further. It's detective work, using clues from one part of the galaxy to understand objects in another, connecting dots across vast distances through the universal language of chemistry. There's also a speculative connection to the debris train hypothesis we explored earlier. If ATLAS is part of a fragmented planetary system, if it's a piece of a super-Earth or mini-Neptune that was destroyed or ejected during formation, or through some later catastrophe, then its chemistry should reflect planetary processes, not just simple cometary ones. Comets are primitive, leftover building blocks from planetary formation, relatively unchanged since they condensed from the protoplanetary disk. But planetary atmospheres undergo complex evolution over billions of years. Outgassing from the interior brings up volatiles trapped in the mantle and core. Photochemistry from stellar radiation breaks apart molecules and creates new ones. Impacts from asteroids and comets deliver fresh material from outside. An object like ATLAS, if it's a planetary fragment rather than a pristine comet, might carry signatures of those processes, chemical or isotopic anomalies that betray a more complex history. Testing this requires isotopic analysis, high-resolution spectroscopy that can measure not just what molecules are present, but the relative abundances of their isotopes. Deuterium to hydrogen ratios, carbon-13 to carbon-12, oxygen-18 to oxygen-16. These ratios vary depending on formation temperature, because lighter isotopes preferentially escape or react at different rates than heavier ones. They vary depending on radiation environment, because cosmic rays and stellar ultraviolet can alter isotopic compositions through spallation and photodissociation. They vary depending on time since formation, because radioactive decay changes ratios over millions or billions of years. These isotopic fingerprints are unique to each object's history, a record written in the relative abundances of atoms that can be read if you have sensitive enough instruments. JWST can measure some of these ratios in bright comets, when they're active and their comas are large enough to provide strong spectroscopic signals. If ATLAS remains bright enough at perihelion, if it doesn't disintegrate under the intense solar heating, if it survives its close pass, we might get those measurements. Astronomers are already planning observing campaigns, scheduling JWST time around perihelion, coordinating with ground-based telescopes to maximize coverage. Those measurements could tell us whether ATLAS is just a comet, unusual but fundamentally similar to the icy bodies in our own Oort cloud, or something more complex, a fragment of a world that never finished forming, or a piece of a planet that was torn apart. The exoplanet connection also raises philosophical questions about diversity and probability. We're discovering that planetary systems come in every imaginable configuration. Hot Jupiters, orbiting closer to their stars than Mercury orbits the Sun. Super-Earths that have no analogue in our solar system. Mini-Neptunes with thick hydrogen atmospheres. Planets orbiting binary stars, triplets, even systems with 4 or 5 stars. Systems with planets in resonance, locked in gravitational dances. Systems where planets have migrated, leaving gaps and patterns in the disk. The diversity is staggering, far greater than anyone expected when the first exoplanets were discovered. If planetary systems are this diverse, if formation conditions vary so wildly from star to star, then interstellar objects should be equally diverse. ATLAS might be strange compared to solar system comets, but maybe it's typical for its home, system. Maybe where it came from, carbon dioxide-rich comets are common, water-poor ones the norm. Maybe the 17 comets clustering around it, if they're related, if they share a common origin, come from a system where fragmenting planets or massive collisions created swarms of debris, fleets of objects ejected into interstellar space. We're used to thinking of our solar system as the template, the standard against which to measure everything else. But exoplanet science is teaching us that our system might be unusual, possibly even rare in some of its characteristics. In the next section, we're pivoting to fusion energy, another frontier where humanity is trying to harness the power of the stars, bringing stellar processes down to Earth scale. The connection to comets is metaphorical, not literal, but metaphors can illuminate unexpected parallels. Comets are engines, burning through volatile fuel as they approach the sun, releasing energy in the form of light and gas. Fusion reactors are engines, burning through hydrogen fuel to produce energy, releasing it as heat and radiation. Both involve phase changes, thresholds where systems transition from stable to active. Both involve heat transfer, energy flowing from hot regions to cold. Both involve runaway reactions, feedback loops where initial changes amplify themselves. Both pulse with energy when conditions are right. And both might teach us something fundamental about how the universe manages energy on scales from the microscopic realm of atomic nuclei to the cosmic realm of planetary systems and beyond. Part 13. Fusion Energy and Stellar Parallels. 2025 has seen progress in fusion energy, the decades-long quest to replicate the sun's power on Earth. Fusion, the process where light atomic nuclei combine to form heavier nuclei and release energy, is what powers stars. It's clean, abundant, potentially limitless, and extraordinarily difficult to achieve in a controlled way. For 70 years, scientists have been chasing this dream, building ever larger machines, refining techniques, pushing closer to the threshold where fusion becomes practical. And laboratories around the world are finally getting closer, crossing milestones that seemed impossibly distant just a decade ago. Recent experiments at facilities like the National Ignition Facility in the United States and JET, the Joint European Torus in the United Kingdom, have achieved net energy gain, producing more energy from fusion reactions than was put in to initiate them. This is a milestone that cannot be overstated. It doesn't mean commercial fusion power is around the corner. There are still enormous engineering challenges to overcome, questions of efficiency, sustainability, material durability. But it proves the concept works at a fundamental level. You can take a tiny pellet of hydrogen isotopes, deuterium and tritium, compress it with powerful lasers, or confine it with magnetic fields, and get it hot and dense enough to fuse. The result is a burst of energy, a miniature star flickering to life for a fraction of a second, releasing neutrons and heat that can, in principle, be captured and converted to electricity. The physics of fusion has surprising parallels to the physics of comets, connections that seem abstract at first, but reveal deeper similarities when you look closely. Both involve phase changes driven by external energy inputs. Both require crossing thresholds where systems transition from stable to active states. Both are governed by feedback loops where initial changes amplify themselves, creating runaway processes that can be spectacular or catastrophic, depending on how they're controlled. In fusion, you're forcing hydrogen into a plasma state, the fourth state of matter, where atoms are stripped of their electrons. You're heating the plasma to millions of degrees, temperatures where the thermal energy of particles overcomes the electromagnetic repulsion between positively charged nuclei. At those temperatures, nuclei move fast enough to collide with sufficient energy to tunnel through the Coulomb barrier, the quantum mechanical wall that normally keeps them apart. When they tunnel through, when they fuse, they release energy according to Einstein's famous equation, mass converting to energy with devastating efficiency. In comets, you're doing something conceptually similar but at vastly different scales. You're heating ice, forcing it to sublimate from solid directly to gas without passing through a liquid phase. Solar radiation provides the energy, electromagnetic waves hitting the comet's surface and transferring momentum to water molecules, carbon dioxide molecules, frozen volatiles locked in the matrix. As temperature rises, molecules gain enough kinetic energy to break free from the ice lattice. They escape into space, releasing volatiles that form the coma and tail, the glowing envelope and streaming debris that make comets visible across millions of kilometers. The scales are different. Fusion happens at nuclear scales measured in femtometers, sublimation at molecular scales measured in nanometers. But the underlying principle is remarkably similar. Add energy, cross a threshold, and you get a runaway process. In fusion, the energy released by initial reactions heats surrounding fuel, causing more reactions, creating a chain that sustains itself if conditions are right. In comets, the gas released by initial sublimation can trap heat beneath the surface, warming deeper layers, driving more sublimation in a feedback loop that accelerates as the comet approaches the sun. Comets are engines already in motion, carrying their fuel with them across the void. They carry water ice, carbon dioxide ice, frozen methane, ammonia, complex organic compounds, all bound together in a loosely consolidated matrix. As they approach the sun, solar radiation heats the surface. The intensity of that radiation follows an inverse square law, doubling in strength every time the distance halves. So a comet at 2 astronomical units receives 4 times more radiation than one at 4 astronomical units. This creates a natural acceleration, a build-up where outgassing intensifies as the comet gets closer. Ices sublimate, gas escapes, the coma grows, expanding outward like an atmosphere but without gravity to hold it in place. The process accelerates as the comet nears perihelion because radiation intensity increases with proximity. At some point, the comet reaches peak brightness, maximum outgassing, a crescendo where the engine runs at full throttle. Then it begins its retreat, moving away from the sun on the outbound leg of its orbit, cooling down, the engine throttling back and eventually shutting off until the next orbit brings it inward again. Atlas's outgassing behaviour is unusual precisely because it activated early, at 2.9 astronomical units, farther from the sun than most comets begin their displays. Most comets don't start outgassing noticeably until they're inside 2 astronomical units, closer to Mars's orbit. But Atlas was already pouring water vapour into space when it was well beyond that threshold, acting like a fire hose at a distance where most comets are still dormant. What triggered Atlas's early ignition? What crossed its threshold before it should have? Maybe it's compositionally different, rich in super-volatile ices like carbon monoxide that sublimate at lower temperatures than water or carbon dioxide. Carbon monoxide ice turns to gas at around minus 200 degrees Celsius, far colder than water ice, which requires minus 100 degrees or warmer. If Atlas is loaded with carbon monoxide, it could start outgassing while still distant. The super volatiles escaping first and dragging water and other compounds along in their wake. Maybe it has internal heat, energy stored from its formation, or generated by radioactive decay of elements like aluminum-26 or potassium-40. These isotopes release heat as they decay, warming the interior over millions of years. If Atlas formed in an environment rich in such isotopes, or if its interior never fully cooled after formation, that residual heat could drive sublimation from the inside out, creating activity at distances where solar radiation alone wouldn't suffice. Or maybe it's been spinning up, rotational energy converting to heat through tidal friction or stress fractures in its structure. If Atlas is a loosely bound rubble pile, pieces grinding against each other as it tumbles, that friction generates heat. Over time, over the long journey through interstellar space, that heat could accumulate, warming the interior, preconditioning the comet for early activity when it finally encounters a star. Fusion reactors face a similar challenge, one that's consumed decades of research and billions in funding. You need to ignite the fuel, get it hot enough to start fusing, and then maintain those conditions long enough for the reaction to be self-sustaining. This is called ignition, the holy grail of fusion research, the point where the energy released by fusion heats the surrounding fuel, which then fuses, releasing more energy, in a feedback loop that continues without external input. Achieving ignition is extraordinarily hard because plasma is unstable, a roiling chaotic soup of charged particles that defies confinement. Plasma wants to cool, to expand, to lose the extreme conditions necessary for fusion. It's like trying to hold lightning in a bottle, except the bottle has to be invisible because any physical wall would instantly vaporize at plasma temperatures. So you use magnetic fields, invisible force fields that shape and squeeze the plasma, or you use inertial confinement, lasers that compress fuel pellets so rapidly that fusion occurs before the plasma has time to disperse. Both approaches are engineering marvels, pushing the limits of what's possible with current technology. Could something similar be happening with ATLAS? Could its outgassing be self-sustaining, driven by feedback between sublimation and heat transfer in ways that amplify activity beyond what solar radiation alone would produce? Normally, comets cool themselves by outgassing. The sublimation process is endothermic, absorbing heat from the surroundings, like sweat cooling your skin through evaporative cooling. This acts as a thermostat, preventing runaway heating. But if the gas gets trapped, if it forms a pressurized layer beneath the surface, because the upper crust is too dense or compacted to let it escape freely, it could insulate the interior, trapping heat and driving more sublimation. Pressure builds, temperature rises, more ice sublimates, and suddenly you have a runaway effect. A comet that outgasses more vigorously than expected for its distance from the Sun. The insulating layer acts like the magnetic confinement in a fusion reactor, except instead of confining plasma, it's confining heat and pressure until they reach critical thresholds. This is speculative, a hypothesis without detailed thermal models to support it. We don't have temperature maps of Atlas's interior, don't have measurements of its internal pressure gradients or the permeability of its crust. But the analogy to fusion is useful, not because it proves anything, but because it provides a framework for thinking about energy balance, thresholds, feedback loops. Both comets and fusion reactors are systems where energy input crosses a threshold and triggers a self-amplifying process. Understanding one might shed light on the other, cross-pollinating insights between fields that rarely talk to each other. Engineers studying fusion learn about confinement, how to contain extreme conditions long enough for desired reactions to occur. They learn about instability, how plasma develops turbulence and hotspots that disrupt the smooth flow of energy. They learn about energy balance, the delicate equation where input must match or exceed output for the system to break even. Astronomers studying comets learn about sublimation, the quantum mechanics of phase transitions and molecular escape velocities. They learn about thermal conductivity, how heat propagates through porous ice mixtures. They learn about volatile transport, how gases move through fractures and voids in cometary nuclei. The physics overlaps more than you'd think, both dealing with extreme conditions, phase transitions, energy cascades. There's also a metaphorical connection to the solar system itself, one that captures the sense of mystery surrounding the comet pulse. Is the system undergoing a kind of ignition, a burst of activity triggered by Atlas's arrival? Are the 17 comets like fuel pellets in a fusion reactor, ignited by proximity to an external energy source, responding to something Atlas carries or radiates? This stretches the metaphor to breaking, pushes it past where science can follow, but it captures something important, the intuition that something is happening, something we don't fully understand. Whether it's physical or perceptual, coordinated or coincidental, we don't yet know. But the system feels alive, pulsing with motion and energy, like a reactor on the edge of ignition, hovering at the threshold where stable becomes unstable, where dormant becomes active. That feeling might be illusion, pattern-seeking minds finding order in randomness, or it might be signal, a genuine physical phenomenon waiting for the right measurements to reveal its nature. We won't know until we cross our own threshold, accumulating enough data to tip the balance from uncertainty to understanding. In the next section, we're going to talk about artificial intelligence in astronomy, the tools that are transforming how we detect and interpret cosmic phenomena. Because AI might be the key to understanding the comet pulse, either by confirming it's real or by revealing the biases in our observations. AI doesn't have human intuition, the gut feelings that sometimes lead to breakthroughs, but it doesn't have human blind spots either, the cognitive biases that make us see patterns where none exist. It sees patterns we miss, and misses patterns we invent. And that dual nature makes it both powerful and dangerous, a tool that could solve the mystery or deepen it, depending on how we wield it. Part 14, AI in Astronomy. Astronomy is drowning in data. Modern surveys generate terabytes of images every night, millions of detections, thousands of alerts. Human astronomers can't process it all. They need help, automated systems that can sift through the noise, flag interesting events, and prioritize follow-up. Artificial intelligence, specifically machine learning, has become that help. But it's not just a tool, it's reshaping how we see the sky, redefining the boundary between observation and interpretation, and raising uncomfortable questions about whether we're discovering patterns or creating them. A recent study from Oxford and Google Cloud demonstrated this shift in dramatic fashion. Researchers trained a general-purpose AI model, Gemini, to classify cosmic events. They fed it images of transients, supernovae, variable stars, asteroids, comets, and asked it to identify what each object was. The model performed remarkably well, not just matching the accuracy of specialized algorithms that had been hand-tuned for specific tasks, but explaining its reasoning in ways that humans could understand and evaluate. It could say, this looks like a supernova because of the light curve shape and the lack of proper motion. This looks like a comet because of the diffuse coma and the tail direction. The ability to explain is crucial. It means astronomers can audit the AI's decisions, catch mistakes, understand biases. It transforms AI from a black box into a collaborator, something that doesn't just give answers but shows its work. This matters because trust requires transparency. If an AI flags an object as interesting, and astronomers spend telescope time following it up, they need to know why the AI made that decision. Was it based on physical characteristics that make sense? Or did the AI latch onto some spurious correlation, some artifact in the training data that has nothing to do with real astrophysics? Explainable AI helps separate signal from noise, genuine insight from algorithmic hallucination. Another Oxford study focused on filtering supernova alerts, addressing a different but equally pressing problem. The volume of alerts from modern surveys is overwhelming. Most are false positives, artifacts from image processing, cosmic rays hitting the detector, misidentified asteroids, satellites streaking through the frame. Astronomers spend hours each night manually checking alerts, discarding the junk, saving the real events. It's tedious work, necessary but exhausting. The AI filter reduced that workload by 85%, catching the false positives automatically and letting the real supernovae through. 85% less time wasted means more time for actual science, more time for thinking instead of sorting. But automation comes with a cost, and that cost is subtle. AI introduces biases, not through malice but through learning. It learns from training data, and if that data is incomplete or skewed, the AI inherits those flaws. Imagine training an AI on a dataset where most comets are faint and most asteroids are bright. Perhaps because bright comets are rare or because the survey that generated the data was optimized for asteroid detection. The AI might learn to associate brightness with asteroids and faintness with comets. Then when it encounters a bright comet, something unusual like Atlas, it might misclassify it as an asteroid. The mistake wouldn't be obvious unless someone checked. And if the AI is processing millions of objects, who has time to check them all? Worse, AI can create patterns where none exist. If the model sees a cluster of alerts in a specific region of sky, perhaps because that region was observed more frequently, or under better seeing conditions, it might flag that region as interesting, drawing more attention to it. Astronomers follow up, discover more objects in that region, and the cluster becomes real, at least in the sense that it's recorded and catalogued. But was the cluster there to begin with, a genuine overdensity of objects? Or did the AI amplify a statistical fluctuation into a perceived signal, creating a feedback loop where attention begets discovery begets more attention? This is directly relevant to the comet pulse we've been investigating. If AI algorithms are processing the survey data, flagging comets, clustering alerts, they could be shaping what we see in profound ways. The 17 comets might be real objects on real orbits, no question about that. But the impression of synchrony, the sense that they're moving together in some coordinated fashion, might be amplified by how the AI groups them. The AI doesn't know about Atlas. It doesn't have a narrative about interstellar visitors triggering pulses. But it does have thresholds, decision boundaries, patterns embedded in its learned representations. Those patterns, artifacts of training rather than reflections of physical reality, could create clustering where none exists. Consider how an AI processes time series data. It looks for correlations, periodicities, synchronized events. If 17 comets happen to reach detectable brightness during a narrow time window, The AI might interpret that as significant, even if the timing is purely coincidental. It might group those comets together in its internal representation, assign them similar classification scores, and present them to astronomers as a related set. The astronomers seeing this grouping might then look for physical explanations, mechanisms that could tie the comets together. And suddenly you have a pulse, a phenomenon that emerged not from the sky, but from the interaction between data and algorithm. Testing this requires transparency and redundancy. We need to see how the AI makes decisions, what features it uses, what weights it assigns to different characteristics. We need to run the same data through different models, see if the clustering persists or changes. If multiple independent AIs, trained on different datasets with different architectures, all see the pulse, that's stronger evidence it's real. If the pulse appears only with certain models or certain training datasets, that's evidence it's an artifact, a ghost in the machine rather than a signal from the cosmos. There's also the intriguing possibility that AI could predict phenomena before we observe them. Imagine an AI trained on decades of comet observations, learning the patterns of infall, the statistical distribution of arrivals, the subtle periodicities buried in noisy data. If that AI predicted a burst in 2025 before it happened, before Atlas was discovered, before any of the 17 comets were detected, that would be remarkable. It would suggest the burst is part of a larger pattern, something periodic or quasi-periodic that the AI detected in the historical data, a pattern too subtle for human analysis but clear to a system that can process thousands of orbits simultaneously. We don't have that prediction, as far as anyone knows. No AI announced in 2024 that 2025 would see an unusual comet cluster. But the fact that we don't have such a prediction is informative. It suggests either that the pulse is genuinely anomalous, outside the bounds of historical patterns, or that it's not significant enough to stand out statistically, just normal variation in comet rates that looks unusual when you squint at it the right way. Future surveys, with more data and better AI, might be able to forecast comet activity the way meteorologists forecast weather. They'd train models on centuries of observations, incorporate physical models of Oort cloud dynamics, account for known perturbers like passing stars and galactic tides. These models would generate probabilistic predictions, confidence intervals around expected comet fluxes. When observations deviated from predictions, that deviation would be meaningful, a genuine anomaly requiring explanation. Right now, we're not there yet. We're still in the era where we discover comets as they arrive, react to events rather than anticipate them. AI in astronomy is a double-edged tool, amplifying both our capabilities and our limitations. It amplifies our capabilities by letting us process data at scales we couldn't manage manually, finding needles in haystacks, detecting faint signals buried in noise, but it also amplifies our biases, codifying assumptions into algorithms that then shape what we observe. If we train AI on data from surveys that favour certain types of objects or certain regions of sky, the AI will inherit those preferences and reinforce them, creating blind spots we might not notice. The comet pulse, whether real or illusory, is a test case for this new era of AI-mediated astronomy. It's a pattern at the edge of significance, where data meets interpretation, where observation meets cognition. And AI sits at that boundary, mediating between the sky and our understanding of it, translating photons into knowledge, but also, potentially, introducing distortions we're only beginning to recognise. The question we're left with is philosophical as much as scientific. When we look at the sky through AI, are we seeing the sky itself, or are we seeing the sky filtered through the AI's learned representations? The answer is probably both. The sky is real, the photons hitting our detectors are real, the orbits of comets and interstellar visitors are governed by real physical laws. But our perception of patterns, our sense of what's significant and what's noise that's mediated by tools that have their own biases and limitations. In the final section, we're going to touch on the wildest edge of physics, the search for new forces, new particles, phenomena beyond the standard model. Because if the comet pulse is real, if it reflects genuine physical coupling between Atlas and the solar system, then maybe we're seeing hints of something deeper, something that forces us to expand our understanding of how the universe works. Or maybe we're just seeing noise, amplified by algorithms into the appearance of signal. But asking the question, pushing the boundaries, testing the limits of what we know, that's how science moves forward. even when the answer is we don't know yet. Especially when the answer is we don't know yet, because uncertainty is where discovery lives, in the gap between what we've measured and what we understand, in the space where data meets theory and neither quite fits. That's where we are with the comet pulse, and that's exactly where we need to be. Part 15. Physics Edge. News. The fifth force. The standard model of particle physics is one of the most successful theories in science. It describes how particles interact through four fundamental forces: electromagnetism, the strong nuclear force, the weak nuclear force, and gravity. It predicts the existence of particles that were later discovered, like the Higgs boson. It explains phenomena from atomic structure to the behaviour of the early universe, but it's incomplete. It doesn't account for dark matter. It doesn't explain gravity at quantum scales. And there are hints, tantalising, frustrating hints, that something is missing. One of those hints comes from the Muon-G-2 experiment. Muons are particles similar to electrons, but about 200 times heavier. They have a property called magnetic moment, which describes how they interact with magnetic fields. The standard model predicts the muon's magnetic moment to extraordinary precision, down to 10 decimal places. But recent experiments have measured it and found a small discrepancy, a deviation of a few parts per million. It's tiny, but it's persistent. Multiple experiments see the same anomaly. If the discrepancy is real, if it's not just a statistical fluctuation or a calibration error, it could indicate the existence of new particles or forces not included in the standard model. Maybe there's a new boson, a particle that mediates an unknown force, interacting with muons in ways we haven't accounted for. Maybe dark matter particles are coupling to ordinary matter more strongly than we thought. Or maybe the standard model calculations are wrong, missing some subtle effect that becomes significant at high precision. There are other hints too, anomalies in the decay of B mesons, particles containing bottom quarks, tensions in the measurement of the Hubble constant, the rate at which the universe is expanding, unexplained signals in dark matter detectors. None of these are definitive. Each could be explained by mundane causes, experimental error, unaccounted systematics, statistical noise, but taken together, they create a sense of unease, a feeling that we're missing something fundamental. Could there be a fifth force, something beyond electromagnetism, gravity, and the nuclear forces? A force that operates at specific scales, maybe cosmic scales, influencing the motion of objects over vast distances? This is speculative territory, the kind of idea that gets discussed in theoretical papers with lots of question marks, but it's not impossible. The universe has surprised us before. Dark energy, the mysterious force accelerating cosmic expansion, was completely unexpected. Maybe there are other forces waiting to be discovered, too weak to detect in laboratory experiments, but strong enough to matter over astronomical distances. Apply this to the comet pulse. If there's a new force, one that couples to icy bodies or objects with specific compositions, maybe ATLAS is interacting with the 17 comets through that force. Not gravity, not electromagnetism, but something else. This force would have to be extraordinarily weak, undetectable in solar system dynamics we've already mapped. But maybe it manifests only under specific conditions, when objects with the right properties come into proximity, when velocities or temperatures cross certain thresholds. Testing this requires looking for anomalies in comet motion, deviations from predicted orbits that can't be explained by known forces. We'd need high-precision astrometry, tracking the comet's positions to within kilometres over weeks or months. We'd look for accelerations, changes in velocity that don't match gravitational perturbations from the planets or the Sun. If we found such anomalies, and if they correlated with Atlas's position, that would be evidence of coupling, something tying Atlas to the other comets in ways we don't understand. So far, no such anomalies have been reported. The comets appear to be following ballistic trajectories, obeying Newton's laws and Einstein's corrections. But the observations are incomplete. Most of the 17 comets are faint, observed only a handful of times, their orbits determined with large uncertainties. Anomalies, if they exist, might be hidden in the noise, waiting for better data to reveal them. There's also the possibility that new physics operates not through forces, but through fields, subtle variations in space-time or fundamental constants that affect how objects behave. Imagine a field that modulates the sublimation rate of ices, making some comets outgas more vigorously when they're near objects like Atlas. Or a field that alters orbital energy slightly, nudging comets toward or away from the Sun in ways that accumulate over time. These fields would be almost impossible to detect directly, but they'd leave fingerprints in the statistics, correlations between comet properties and proximity to interstellar objects. This is the frontier where physics meets philosophy. We're asking whether the laws we know are complete, whether the universe operates only through the forces we've catalogued, or whether there are deeper layers, hidden mechanisms that only reveal themselves under rare conditions. The comet pulse, if it's real, if it's physical, could be one of those conditions. Or it could be nothing, a coincidence that dissolves under scrutiny, a pattern we invented because we wanted the universe to be more interesting than it is. But here's the thing, the universe is already interesting. Gravitational waves rippling through space-time, exoplanets with atmospheres we can taste from light years away, fusion reactors igniting on Earth, miniature stars in bottles, AI learning to see the sky the way we do, finding patterns we miss, missing patterns we find. And somewhere out there, an interstellar visitor named Atlas, carrying chemistry that doesn't quite fit, moving through a crowd of comets that may or may not be connected to it, leaving us with questions we're only beginning to frame. So where does that leave us? With data that's ambiguous, theories that are incomplete, and a mystery that refuses to resolve cleanly. The comet pulse might be real, it might be an artifact, it might be both, a genuine configuration of orbits amplified by how we observe and interpret. We won't know for certain until we have more data, better observations, clearer models. Perihelion is approaching, October 30th, 2025. Atlas will reach its closest point to the Sun, and we'll have our best chance to study it up close. Spectroscopy, imaging, astrometry. Every instrument we have will be pointed at this visitor, trying to extract its secrets. The 17 comets will continue their journeys too. Some will fade as they move outward, cooling and dimming until they're lost to observation. Others will brighten, approaching their own perihelia, giving us opportunities to study them in detail. We'll compare their chemistries, their orbits, their behaviours. We'll look for family resemblances, for shared origins, for evidence of streams or waves or perturbations. We'll test the hypotheses we've laid out, Oort cloud waves, debris trains, dark perturbers, each one making predictions we can check against reality. And maybe, in a few months or years, we'll have an answer. Maybe the pulse will be explained, reduced to coincidence and bias and the ordinary workings of celestial mechanics. Or maybe it won't. Maybe we'll find something genuinely strange, a coupling we didn't expect, a mechanism that forces us to revise our understanding. Either outcome is valuable, either outcome teaches us something, but for now, in this moment, we're left with the question. The solar system seems to breathe. 17 comets pulse inward, as an interstellar visitor crosses through then scatter as it departs. Is it real? Is it spooky? Or is it just the universe reminding us how much we have yet to learn? You've seen the facts, the peculiarities of Atlas, the water pouring into space, the carbon dioxide coma, the possible glow. You've seen the crowd, the 17 comets clustering in time, their names and orbits and the surveys that found them. You've seen the simulations, the way projection and compression can create illusions, and the tests we'd need to see past them. You've explored the hypotheses, from Oort cloud waves to debris streams to dark perturbers to artificial objects to observer bias. You've looked at the wider universe, the gravitational waves pulsing through space-time, the exoplanet atmospheres revealing alien chemistries, the fusion reactors igniting in laboratories, the AI algorithms reshaping how we see the sky, the hints of new physics at the edges of the standard model. Now it's your turn. How weird do you believe? Is the pulse a message, a signal of something profound happening in the solar system? Or is it a mirage, a trick of perspective and timing that will evaporate when we look closer? The data doesn't force an answer yet. The universe is holding its cards close the way it always does, making us work for every revelation. But that's the beauty of it. That's why we keep looking up, keep building better instruments, keep asking uncomfortable questions. Because sometimes just sometimes, the universe answers. And when it does, when we catch a glimpse of something we didn't expect, something that changes how we see reality, it's worth every hour spent staring at ambiguous data, every moment of uncertainty, every theory that collapsed under scrutiny. The comet pulse, whatever it is a reminder. We live in a universe that still has the power to surprise us, and that, more than any single answer, is what keeps us searching. The solar system breathes, and we're listening, trying to hear what it's telling us. The story isn't over. Perihelion is coming. The data will sharpen. The models will improve. And somewhere in that future, clarity might emerge. Until then, we wait, we watch, we wonder. Because that's what we do. That's what we've always done. And the universe, indifferent but endlessly fascinating, keeps spinning its mysteries, daring us to solve them.